This is the video for Part 1 of Section 3.3, Isomorphisms and Homomorphisms. In this section, we want to consider equivalence of rings. As we'll see, two rings can have very different representations, but be essentially the same, meaning that they have the same arithmetic structure. We'll start with an example. So consider the subset S, consisting of the even integers mod 10. So containing 0, 2, 4, 6, and 8. We want to construct the addition and multiplication tables for this subset with the elements listed in the order shown. So we're going to list the elements 0, 6, 2, 8, and 4. So on the left we have the addition table, on the right we have the multiplication table. So in the addition table, when we add 0 to any of the elements, we obtain the same element back. And then in the second row, well, 6 plus 6 is 12, mod 10, that's 2. 6 plus 2 is 8. 6 plus 8 is 14, mod 10 is 4. And 6 plus 4 is 10, which is 0, mod 10. And likewise, we can fill in the rest of the table. In the multiplication table, well, if we multiply 0 times any of the elements, we'll obtain 0. So that fills in the first row and the first column. And then in the second row, 6 times 6 is 36. Mod 10 is equal to 6. 6 times 2 is 12. Mod 10 is 2. 6 times 8 is 48. And mod 10, that's equal to 8. 6 times 4 is 24. And mod 10, that's equal to 4. And then in the third row, well, 2 times 6 is 12, mod 10 is 2, 2 times 2 is 4, 2 times 8 is 16, mod 10 is 6, 2 times 4 is 8. And then we can fill in the fourth and fifth rows likewise. Now we can see from the tables that S is a commutative ring with additive identity 0 and multiplicative identity 6. When we multiply 6 times any of the elements in the subset, we obtain the same element back. We want to compare the ring S with the ring Z5 containing the integers mod 5, 0, 1, 2, 3, and 4, and we've put bars over the elements to differentiate them from the elements in S. So the addition and multiplication tables for Z5 are shown. And suppose we start with the tables for S now. So these are the tables that we constructed earlier. Then replace the elements in the tables for S as follows. 0 will be replaced with 0 bar. 6 will be replaced with 1 bar. 2 with 2 bar. 8 with 3 bar, and 4 with 4 bar. Now examining these, we obtain the tables for Z5. So starting with the tables for S and then replacing the elements as shown, we obtain the tables for Z5. This shows that the ring S is essentially the same as the ring Z5, with the only difference being how the elements are labeled. The ring operations and structure are essentially identical. In this case, we say that the two rings are isomorphic. So in order for two rings to be isomorphic, there must be a one-to-one correspondence or a bijection between their elements so that we can relabel the elements of one ring to obtain the elements of the other ring. More is required, however. The relabeling must be done in such a way that the addition and multiplication tables are preserved. So the bijection must preserve the addition and multiplication. Before giving a formal definition of what it means for two rings to be isomorphic, we'll start by reviewing functions and some of their important properties. So we'll start with the definition of a function. Let A and B be sets. Then a function f from A into B is a rule or correspondence which associates with each element A in A a unique element B in B. The set A is called the domain, and the set B is called the codomain of the function. We denote the function with the notation shown, f colon A and then a right arrow pointing towards B. Now the element B in B associated with an element A in A is denoted f of A, and we write B equals f of A. The element B equal f of A is called the image of A under F. The range of F is the set of all images under F. So this will be the set, it's denoted F with f of capital A, and this is the set of images f of A as A ranges over all elements in capital A. Now note that some texts use the term range in place of codomain and image in place of range. Now we can visualize the function f from A to B by a diagram as follows. So the domain A and codomain B are each represented by an oval. The function f then maps an element A in A into an element B equal f of A in B. So the element A can be represented by a point in the oval corresponding to the domain A, and the function f maps it into a point in the codomain B, and the point B is equal to f of A. The element B is the image of the element A. And the range is the set of all images and is represented by the shaded oval inside the codomain B. In general, not every element in B will be the image of an element in A, in which case the range is properly contained in the codomain B. However, in the case that the range equals the codomain, so that every element of B is the image of an element in A, the function is called surjective. And here's the formal definition. So a function f from A to B is surjective, or is said to map A onto B, provided that for every element B in B there exists an element A in A such that f of A equals B. In symbolic form, f is surjective, provided that for all B in B there exists an A in A such that f of A equals B. So f is surjective, provided that every element in B is an image of some element in A. To show that f from A to B is surjective, we need to show the statement for all B in B there exists an A in A such that f of A equals B. So to prove this, we would start by supposing B is an arbitrary element of B. We then need to show there exists an element A in A for which f of A equals B, or there exists an A in A such that f of A equals B in symbolic form. This is an existential statement, and so to prove this we need to first find an element A and then verify that it satisfies the required conditions. To find A, we usually solve the equation f of A equals B for A. To visualize what it means for a function f from A to be surjective, let's start with an element B in the codomain B. The function is surjective provided that there exists an element A in the domain that maps into B. So we're starting with the element B, and then we have to find an element A that maps into B, that is, for which B equals f of A. A function f from A to B is not surjective, provided that there exists an element B in B that is not the image of any element in A. The range of f will be properly contained in the codomain B, meaning there will be elements in B outside of the range, and we can represent it by a diagram as shown here. So the range is a proper subset of the codomain B, and we have some elements represented by the 2 points there that are outside of the range but still inside the codomain. For our next definition, a function f from A to B is injective, or one-to-one, provided that for all A1 and A2 in the domain A, if A1 is not equal to A2, then f of A1 is not equal to f of A2. In symbolic form, f is injective, provided that for all A1, A2, and A1 not equal to A2 implies f of A1 is not equal to f of A2. This means that f maps distinct elements A1 and A2 in the domain to distinct elements f of A1 and f of A2 in its codomain. Now, to show that a mapping is injective, it's often easier to prove the contrapositive statement, which will be for all A1, A2, and A, f of A1 equals f of A2 implies A1 equals A2. And to prove this, we start by supposing A1 and A2 are arbitrary elements of the domain A. we suppose the hypothesis f of a1 equals f of a2. We then need to show the conclusion a1 equals a2. To visualize what it means for a function to be injective, we'll start with distinct elements a1 and a2 in the domain. These are mapped to distinct elements in the function codomain. So f maps a1 into an element f of a1, and f maps a2 into a distinct element or a different element f of a2. The function is injective provided that this holds for all elements a1 and a2 in the domain. Now a function f from a to b is not injective provided that the negation of the condition in the definition holds. That is, provided that the negation of the symbolic form shown, which is logically equivalent to there exists a1, a2, and a, such that a1 is not equal to a2, but f of a1 equals f of a2. So f is not injective provided that there exist elements a1, a2, and a such that a1 is not equal to a2. So we can see in the diagram we have distinct elements a1 and a2 in the domain, but f of a1 equals f of a2, meaning that f maps a1 to an element f of a1 and f maps a2 to the same element, which is equal to f of a2. That is, there exist distinct elements a1 and a2 in the domain of f that are mapped to the same element f of a1 equals f of a2 in the codomain. And for our final definition of functions, a function that is both injective and surjective is said to be bijective or a bijection. A bijection is also called a one-to-one correspondence. Next, we want to talk about functions associated with rings, and these are going to be called homomorphisms. So suppose R is a ring with operations plus and dot for the addition and multiplication, and S is a ring with operations circle plus and circle dot for the addition and multiplication. So we're using two different symbols for the addition in R and in S, and for the multiplication in R and in S, because in general the two rings may have very different operations. Then a function f from R to S is a homomorphism provided that it satisfies two conditions. The first will denote it Rh1 for ring homomorphism 1, and this is preservation of addition. And this says for all elements a and b in R, f of a plus b is equal to f of a plus f of b. And the second property is Rh2 Preservation of Multiplication, which states for all a, b, and R, f of a times b equals f of a times f of b. Now on the left side of each of these two properties in the definition, a and b are elements in R, so the operations are the operations in R. On the right side, f of a and f of b are elements in S, so the operations are the operations in S. For an example, let's define f from z to z mod n by f of a is equal to the congruence class of a for each integer a. We want to show that f is a homomorphism. So to show this, we need to verify our two properties, Rh1 and Rh2. So Rh1, preservation of addition, will have the form for all a, b in z, f of a plus b is equal to f of a circle plus f of b. Now, a and b are going to be integers, so on the left-hand side, the plus between a and b is just ordinary integer addition. On the right-hand side, f of a and f of b are elements of z mod n, so these are congruence classes, and so the addition on the right side is going to be the addition of congruence classes, which we originally denoted with circle plus. So to prove this, we'll suppose that a and b in z are arbitrary integers, and then we need to show f of a plus b is equal to f of a plus f of b. So starting on the left side, we obtain f of a plus b, and according to the definition of the function f, this will be the congruence class of a plus b. And this is equal to the congruence class of A plus the congruence class of B. That's by the definition of addition in Z mod n. And this is by definition of the function f of A plus f of B. So this equals the right side. We've shown the left side is equal to the right side, so Rh1 holds. Okay, the verification of Rh2 will be similar. Instead of addition, we just have multiplication, and therefore f is a homomorphism. For another example, let's let R and S be any rings, and we'll define f from R to S by f of R is the 0 sub s, the additive identity in S for any R in R. So the function f is mapping every element in the ring R to the additive identity element of S. Then f is a homomorphism. Not a particularly interesting homomorphism, I should say. Okay, to show this, we need to verify Rh1 and Rh2. So again, we'll do Rh1, preservation of addition. And so to prove this, we need to show for all R and T in R, f of R plus T is equal to f of R plus f of T. So for the proof, we'll suppose that R and T in R are arbitrary elements. We need to show f of R plus T is equal to f of R plus f of T. So the left side is f of R plus T, which by definition of our function f is just 0 sub s, the additive identity element in S. And 0 sub s can be written as 0 sub s plus 0 sub s. And this is equal to f of R plus f of T, since each of those is equal to 0 sub s. So we've shown the left side is equal to the right side, so Rh1 holds. And the verification of Rh2 will be similar, and therefore f is a homomorphism.